So hopefully, everyone who's taking this course now, you've taken Calc 1 and 2. So Calc 1 and 2, you covered most things to do with differentiation and integration of one variable functions. All right. So we looked mostly at functions f that send, say, r to r. All right. These are functions of one variable. All right. And these were sufficient for a lot of purposes. So examples, right? Why did we care about these functions? Well, for example, if you have a function x from r to r, might give the trajectory of a particle moving in one dimension, right? So for example, if this is the real line, then you can have a point here. Let's say this is the trajectory at x equals 0, at time equals 0. Your particle, is at some point in the real line, and then at time equals 2, x is another value at the real line. So maybe this is 0, this is 1, this is 2, this is 3, -1, etc. So you could model the particle's progress along this one dimension by looking at its trajectory, right? So the trajectory here is time lives, is a one-dimensional quantity, and you're mapping into a one-dimensional space, a physical line. All right, so we look at this, and then we looked at how derivatives and integrals of this were also physically relevant quantities, right? So derivatives of x of t gave velocity, acceleration, etc. Right? So velocity here would have been dx dt, acceleration would have been the second derivative, and so forth. So that's one example of what you learn to do in calculus. And then there is also a different, different ways that functions of one variable could occur, right? So you could say, let's say f once again is from, say, an interval a to b into r, and let's say f models something, right? So let's say f models the profit f of x at location x, where let's say maybe you only have a one-dimensional sort of consideration of maybe towns that you're selling in. So every single town lies on this one dimension, and at town X, you know that you could sell the profit that your product is making at that location X is f of x. All right, then you could do things like optimization. So which x is profit f of x maximized, minimized, etc. Right. So these are all sort of tools that you've seen in one-dimensional calculus. And you see already how there's significant restrictions here, right? So first of all, it's nice that we have these tools of calculus in one variable to answer these questions so far. But so far, this is very restrictive. Most movement of particles in the real world is not along a real line. It's somewhere in three-dimensional space. And similarly, if you want to optimize things of, say, profit, well, profit parameters are often, not just of a single variable, right? For example, if you were having a profit function, and let's say you're a corporation, you're selling products, and you want to see how the profit of one particular product depends on the location. Well, then the location is probably in 3 dimensions. Once again, it's unique coordinates x, y, and z. So this will be in a function of 3 variables instead of just 1. Or in more realistic economic terms, usually your profit function is going to have a lot of inputs, right? How much money you're making off of a product is some model containing several parameters, maybe even more than 3, right? You gotta put in considerations like, okay, well, maybe the time of year it is, maybe it's a seasonal product, so that's one variable. Maybe there's also the labor input, right? How much it costs in terms of manpower and hiring the manpower to make your product. There is the transportation costs, right? So those are already 3 variables so far. And there's also, innumerable number of variables, right? There's many more variables. There's, the overhead cost of your factories, how much it costs to lease the land, how much gross, how much, well, there's higher order parameters that your profit may depend on. So in any real life scenario, your profit function here is going to depend on many, many more variables than just 1 or 3 or even 50, right? And perhaps more relevant to today's world, you'll find that there's something, if you want to look at how AI works, really at the end of the day, the AI does hinge on something called the cost function. So it's roughly measuring how different, if you're training an AI model, you need to care about how different your AI prediction is compared to what the actual real life scenario is, right? So if the AI predicts some certain thing, you give it a bunch of data, it spits out some result that it predicts it ought to be true in a given situation. You want to compare it when you're training it to something that's actually true in the given situation. That's given roughly by a cost model, which is, how far off you are. So in that case, F would be a function of maybe, millions of parameters, right? Depending on how complex your model is. And then you want to minimize that error, right? To have a very nice model, in which case you need to know how to optimize such functions of very, very high dimension, right? These are still, if you're doing a cost, then it's still a function that maps into one variable, but its input is probably several, dimensions higher than just hundreds of dimensions, thousands, tens of thousands, millions, right? So these are all reasons for us to look ahead at just, at more than just functions of one variable into one dimension. All right, so let me look at chat for a bit. Okay, yeah, I don't know. Yeah, no WebAssign this week. The prerequisites should be listed. And when I say profit, I don't mean, yeah, so this is not an economics course, so very, very, just a vague motivation for why you might care about the math behind this. All right, so profit, I do mean just revenue minus cost, but that's a technicality. You're not expected to know any economics or physics for this class. I may refer to some basic concepts, but they're not testable material. All right, they're just for motivation. So the first task is to generalize this, right? So from what I said, many real life applications are not just functions of one variable to one variable. So, for example, trajectories of particles, roughly speaking, are, in physical space, are functions from one variable. So it should be thought of the time variable to 3 variables. So this is in space. Maybe I'll call this XYZ space or XYZ space. Right, so the picture here is, let's say you have some clock, right? So here's your time, and then you have some trajectory. F of t is now x of t, y of t, z of t. And you're mapping now into physical space. So let me put coordinate axes here. So you're now in XYZ space, the real 3-dimensional world. And so for each particle here, so how you traverse time, let's say you're traversing time here in this direction, then it's going to trace out some sort of path in physical space, all right, where each point on this path, let's say at time, let's say t0, you're at x at coordinates x of t0. Sorry. Actually, let me just do at time equals, let's say 0. You're at some point given to you in coordinates by x of 0, y of 0, z of 0. At some later time, let's say at time equals 2, you're at some other point here where your coordinates are given by x of 2, y of 2, z of 2, for example. All right, in which case you could see that f of t here it's a function of one variable, and what it spits out, component-wise, when you look at the coordinate what the coordinates are, each of these coordinates are described by a function of one variable into the real line, but altogether, right, this is a function, the image is in 3 dimensions. So altogether, this f is a function that maps t, which is 1-dimensional, into x, y, and z, which is 3-dimensional. So trajectories are, physically speaking, probably the simplest model of a function that is not a one-variable function into another 1-dimensional space. It's a one-variable function that maybe takes place in a 3-dimensional space. That's one example of trajectories. Conversely, let's say this is this is roughly the course. This is covered in chapters 10, which we'll begin shortly. Chapters 10 and 12 of our syllabus, and associated with this analysis in chapters 10 and 12, we'll learn how to parameterize these things, how to describe these curves, how to describe these functions of one variable into more than one variable, and we'll also learn to calculate some of the physical quantities associated with these, such as velocity and acceleration. All right. And conversely, you also have other situations, which is, so we've looked at, so trajectories are the prototypical example of functions of one variable into more than one variable. And then, like I said, you also have models for profit, or you could have, say, AA models, etc. They rely on functions of several variables into one variable. So these are functions f that take values in, say, some high dimensional n space. So this is just, R1 is just the real line, R2 is the plane, R3 is XYZ space, and Rn is just n-dimensional space into R. All right, so these are, like I said, the profits or model, your economic model have a lot of inputs. Each of these inputs take up one, is a different dimension you can think of, and it spits out how much your profit is. You could also do sports models, right? As we all know, the Leafs kind of suck. So yeah, if you're the GM of a hockey team, right, you might have some model on how each of your, you have some confident model of how your defensive metrics are, your offensive metrics are, and then your output is maybe like win percentage or something, right? So if you're the Leafs GM, then once again, you're heading in the off season wondering how the hell do you optimize for a better hockey team. Sometimes it's not possible, which might be the case with Toronto, but we don't know. Yeah, so this is the questions here are once again, you want to find ways to optimize f, find its maximum, find its minimum, etc. And we know in one variable, you know how to do this by taking derivatives. Well, in this case, it turns out that there are many derivatives you could take. So one thing we're going to learn is the various derivative quantities we could take, and how this all works out. So we need tools to find max min of f. All right, so this is covered in chapters chapter 14. All right. I should probably say 13 up here too. Okay, so that's basically what the course is going to be for this first half of summer. All right, so the first summer term, which I think is roughly 6 weeks, we're going to focus mostly on these. All right, so it's trajectories of particles and also models of profit and how you might find the maximum and minimum of these. This roughly corresponds to Calc 1. all right, because we're mostly taking derivatives here. We're not going to bother that much with integration, or at least not too involved in integration quite yet, which I know for a lot of you is probably good news. And then maybe for the second half of the class, we're going to look at in full generality, all right? So the first thing we're going to do is looking at functions of several variables into just one variable. You know, how do we calculate the so-called area under the curve, right? Because we could look at now the volume under the graph z is equal to f of xy, and this is in direct direct analog to integration in one variable, right? So in this case, we have x, y, and z. We have the graph of some function, which I'll draw vaguely like this, right? So maybe you have some function that looks like this. And maybe you care about the area under this, or the volume under this in this case, right? So what's the volume? What's the volume under the graph? And this is given by integrals of several variables. And what's the physical manifestation of this? Well, it's basically adding up quantities, all right? So maybe you could think of this as, let's say you're on a two-dimensional plate, xy. At each point, you could say at each point you have a density at that point. Then if you want the total mass of your plate, of some region of the plate that's given by this rectangular outline here, then you can imagine the density of this as being given to you, as a graph over this plate. At each point, the height of it tells you the density. Then integrating this over this two-dimensional region should give you the mass of the plate, all right, when the density is variable. And there are various other applications of this. So this is where integration comes in. And now finally, you also have something that's a bit more complicated. So this is chapter 15, mostly. You're also going to look at, once we do integration, there are integration, tools like change of variable in higher dimensions and different coordinate systems that might be useful in integrating things. So that takes up the bulk of chapter 15. And then finally, we're going to have functions of several variables into more than one dimension. So it's not this in full generality. We'll be mostly considered with something called vector fields, but you'll see the evolution of this of the material here. So we're starting out with something relatively basic, one dimension into many dimensions. Then we also have many dimensions into one dimension, right? And then now, for many reasons, mostly physical reasons, if you're an engineer, you really care about functions that are actually of many dimensions into more than one dimension. So for example, the prototypical example of this is maybe a vector field. The electric field is described by an arrow at each point of space x, y, z, right? So if I have, say, I model my space with coordinates x, y, z, then at every single point here of fixed coordinates, I will assign an arrow. For those of you who've taken physics, and this is a vector. And this vector, or it's an arrow in three-dimensional space. So to tell you which way the arrow points, I need to tell you, I need to basically tell you where the tip of this arrow is. So the tip of this arrow is given to you by the x coordinate of the tip of this arrow, which is, a function, which is p, and I'll call this q. For the y coordinate of the tip of this arrow, and then r for the z coordinate, the component. And each p, q, and r is going to be dependent on where you are in space. So for example, if I move to a different point, x, y, z, I don't expect necessarily that my arrow be the exact same thing, right? Instead, I could allow my arrow to move to point in this direction, for example. And to describe this new direction, my components of this arrow, P, Q, and R, are going to depend on where I am in physical space. All right, so in this case, altogether, this vector field is a function of x, y, z, three dimensions, and it outputs into x, y, z, right? I just call it P, Q, and R, which is also three-dimensional. So these are vector fields in general. They come up a lot in engineering. So then this is mostly, you're going to be able to calculate work done. You're going to calculate surface integrals, something called Stokes' theorems. If you're a physicist or an engineer, then you'll know this as Maxwell's laws. All right, so that's perhaps a big achievement of this type of calculus, it really comes up in the theory of electromagnetism. And this is mostly the conclusion of the class. So this is chapter 16. And like I said earlier, this is maybe, there's a dividing line here where this is term 1 and this is term 2. All right, so that's the rough outline of this class, and hopefully I've given you some general examples. I know they're very sketchy, but hopefully some motivation for why we actually care about these things other than just, doing more math. Let's take a look now at the material for this first part of chapter 10, which is parametrizations in 2 dimensions. All right, so like I said, in general, parametrizations could be into many variables. For now, let's focus on the case of 2 dimensions because it's pretty familiar to us. So these are functions from 1 variable to 2. So in abstract notation, this is a function f from, say, maybe r into r2. But how these are actually written are in terms of coordinate functions. So you're going to get an x coordinate telling you how x varies with a parameter that we're going to call t, and how y varies with a parameter we're going to call t. Okay, so let me give you an example. A graph of a line given by y is equal to mx plus b can be parametrized by x of t is equal to t, and y of t is equal to mt plus b, where t ranges from minus infinity to plus infinity. All right, so this particular case, I have my xy plane here. I have some line with some slope. Well, let's make it a more interesting line. I have a line with some slope here. And what this parametrization tells me is that at t equals 0, and my x is equal to 0, y is equal to b. So this is at x equals 0, y is equal to b at t equals 0. And then as t increases, then I might be traveling along this line here, right? If m is positive, for example, as t increases, t is gonna, x is gonna increase along with t as I go along, and y I'm gonna read off as m times t plus b. So if t equals 1, then I'm gonna be at m plus b, right? So this is, let's say, 1, then this point here is going to be at 1 m plus b. Now, are parametrizations unique? So it's a question for chat. Is there another way I could parameterize this same path? Okay, so there should be another way to parameterize this. So note that parametrizations given any curve in the xy plane parametrizations are not unique. So as an example, for the same line above, we can set the following parameterization. We could set x of t is equal to t minus 1, y of t is equal to m times t minus 1 plus b, which I could simplify this as mt plus b minus m. And this traces out the exact same line. But what's the difference here? Does anyone want to say what the difference between these two parameterizations are? I should probably increase t is also going from minus infinity to infinity. And first I should point out that this traces out the same line, because if I just do the substitution, x is equal to t minus 1, then this tells me y is equal to m times x plus b, which is the exact same algebraic equation of the line here. So somehow I'm traversing the exact same black line I have here. But what's the difference between this and that? Right. So in essence, there is there is a shifting that's taking place. So this is the same as, let me call this A, and let me call this B. So A and B trace out the same path or the same line. Let's call this L. But at t equals 0, A gives the point 0b, whereas B gives the point, sorry for the two B's, but one's capital, one's lowercase. Whereas B gives the point minus, well, okay, so at t equals 0, this is at minus 1, and B minus m. All right, so in the first scenario, you have a point that starts here, at t equals 0. Well, if you start at t equals 0, it starts here and goes there. However, the way I parameterize B, that tells me that's the exact same line. It traces out the exact same line if I let t go from, go through all time. However, at t equals 0, I'm starting somewhere here, right? At x equals minus 1, b minus m, I'm starting here, and I'm going that way. All right, so in essence, a parameterization gives you a little bit more control, or it describes a bit more about what this path is. One other way to think about this is, if let's say your XY plane is a snowy day and this is covered in snow, right? Then you could drive a tractor through this straight line here. Maybe you're clearing the snow or something, you're shoveling the snow, then you're going to clear out the exact same line, path, the image of this line is the same, whether you start shoveling at 6 a.m. or at 6 p.m., right? But the parameterizations might differ if you start at 6 p.m. or 6 a.m., right? Because maybe if you start at 6 a.m., well, if you start at 6 a.m., you might start here at 6 a.m., and then you finish at some later time here. If you start at 6 p.m., well, at 6 a.m., you haven't even cleared any path out yet, and then it eventually progresses starting at 6 p.m. instead. So it sort of gives you more information on precisely, at what time your particle is at what particular point, even though the image might be the same. So the moral of the story is particles may trace out the same path, but have different parameterizations. All right. So let's do maybe another example. So far we've looked at the case for lines. So here's an example of a parameterization given a line. So in general, any graph y is equal to f of x can be parameterized using x is equal to t, y is equal to f of t, right? So, or you could also just shift what x is, right? X could be t plus c for some constant c, and y is just equal to f of just substituting t plus c, or in general, for anything, you could just do or. You could do x is equal to some function like t cubed, y is equal to f of t cubed, etc. Right? So many different parameterizations. You could be creative with these things. And then finally, we could say another classic is parameterizing circles. So I see the question in chat. How does this go from one variable to two? Well, in this case, I'm now describing x as a function of t and y as a function of t. So this is now a map from t into x and y. So in that sense, it's a map from one variable to two, right? When I'm describing this as x is a function of t and y is also as a function of t, what you should be imagining is there's some sort of clock here, right? This is a t clock. It's represented by, it's like some time component here. And as you run through here, it's telling you at each time where you are on this line. So it's a map from one dimension into two-dimensional space because there's x and y coordinates here. All right. Note that I haven't justified why this is better or why this is, why we, I haven't justified quite yet, why parameterization is better or why we need to do this. That I'm just pointing out that the framework is, we've previously only considered functions from one variable to one variable. In this case, parameterizations are into two dimensions are from one variable t into two variables x and y. All right, we'll get into why these things are useful later on. Well, pretty soon. All right, so let me show some parameterization of circles. I know this is not the most intriguing stuff, but these are the building blocks for what we'll be looking at later, so it's pretty useful. So recall a circle of radius, let's say R0, centered at x0, y0, is described as x minus x0 squared plus y minus y0 squared is equal to r0 squared. Right, that's your classic equation of a circle. So how might we generalize this into parameterization? Well, this could be parameterized as x of t and y of t are equal to cosine of t plus x naught. And, oh, sorry, this should be r0 cosine of t plus x naught, and r0 sine of t plus y naught. Let's say t is, once again, a real number. So how could we check this is a parameterization? Well, we could check by saying, well, x of t minus x0. So let's check, does this satisfy the algebraic equation for the circle? Well, you could try it, right? So this is x of t minus x0. This is just going to be r0 cosine t. Y of t minus y0 is just going to be r0 sine t, right? So these two facts give you together that x of t minus x0 squared plus y of t minus y0 squared is equal to r0 squared cos squared t plus r0 squared sine squared t. And what's cos squared t plus sine squared t? Let me think back to your trig identities. Right, so this is just going to be equal to r squared cos squared t plus sine squared t, which is 1, so it's just r0 squared t, right? So you see that this parameterization in t, when we find creative ways of eliminating t just so that we get a function relating x and y together, well, in this case, x and y do satisfy the equation r0 squared, which is exactly the equation we had for a circle of radius r0 centered at at x0, y0, right? So these do match, which means that this parameterized equation does trace out the path that I claim it does, which is a circle of radius r0. All right, so let me draw a picture here. Let's say I'll set this to be a circle, which is x0, y0 is equal to 0, 0. All right, so I'm just going to care about the circle center at the origin for now. And let's say the radius here is just 1, all right? So here's a picture for the above. Then in this parameterization, where am I at t equals 0? What coordinate am I? Where do I start? Do I start here? Do I start here? Do I start here or here? Or somewhere in between? This is the x-axis and this is the y-axis. Where are the xy coordinates at t equals 0? So yeah, t equals 0, I'm starting the clock and seeing where my particle is. So I plug this in, right? These are all 0, the way I set this up here. I want to parameterize this circle, and it's at radius 1. So this is x is equal to cosine t, y is equal to sine t. So at t equals 0, what's x and y? Right, almost. It's not quite 0, 1, but it's the reverse. It's 1, 0. So at 0, 0, I start at this point here. At t equals 0, you're at x, y is equal to 0, or is equal to 1, 0. Right, because cosine of 0 is 1 and sine of 0 is 0. Now, what happens at, say, time is equal to pi over 2? So that's pi over 2 radians, that's 90 degrees. All right, so cosine of 90 degrees is at 0, and what's sine of 90 degrees? Well, you know that, well, one way we can see this cosine squared plus sine squared equals 1. So if one of them is 0, then the other one has to be 1. So you know that at t equals 1, or sorry, at t equals pi over 2, xy is equal to 0, 1. All right, and so forth. You could see at t is equal to, say, pi. You could check cosine of pi. It's going to be equal to minus 1. So at t equals pi, xy is equal to minus 1, 0, and so forth. So which way am I traversing this circle according to this parameterization? Am I going counterclockwise or clockwise? Am I going this way or this way? Right. So in this case, I'm traversing this circle counterclockwise. All right. So I've seen that t between, so let's say t is between, well, it's all of the reals right now. So at t equals 0, so this traces out a radius 1 circle centered at the origin, starts at, so at t equals 0, xy is equal to 1, 0, and this parameterization traces out the circle counterclockwise. All right, so we have a question about two parameterizations of a circle. All right, yeah, let's do a variant of this. This will come and use, this is pretty, you'll see this pretty frequently later on. So it's useful to figure out how to parameterize circles a lot in this class. What is another parameterization for the same circle starting at, so for the same circle with x at time equals 0, y at time equals 0, at 1, 0, but clockwise. Does someone have a suggestion for what this parameterization might be? So I want the same image, the same unit 1 circle here, centered at 0, 0. I want to start, well, at time equals 0, I also want to begin at the point 1, 0. But instead of going this way, I want to go this way. Right, so I could reverse sine and cos with x and y. But frequently, another way to do this is you could also just do, so the issue with switching cosine and sine, right, is if you just switch sine and cosine, well, at sine of 0, you're going to get x is equal to 0. And at y, if at cosine equals 0, you're going to get 1. So if I just switch this, I'm going to start at this point, and I no longer start at this point. So while switching cosine and sine does get you something counterclockwise, it doesn't let you, if you don't do anything to t, it doesn't let you start at 1, 0 anymore, right? But instead, what you could do is you could do cosine t and sine of minus t. But because sine is an odd function, sine of minus t is the same thing as minus sine t. And then you could check that at t is equal to 0, you once again have 1 here. At sine, so you at t equals 0, you once again have 1 here and 0 here. But then say at t is equal to pi over 2, at 90 degrees, you have x is equal to 0, which is great. And then you have minus sine of 90 degrees, which is minus 1. So you end up down here. So instead of going from here to here, you go from here to here. So you're actually going you're going over clockwise. By the way, you could also switch cosine and sine, like is suggested in chat. But to do that, you're going to have to play around with your parameter t, so that at time equals 0, if you want, at time equals 0, you have to start at this point. So if I let x equal sine of t and y is equal to cosine of t, well, then I might have to shift time by t plus pi over 2. Yeah, you might have to do sine t plus pi over 2 and cosine t plus pi over 2 to make sure that at t equals 0, you're at cosine pi over 2, or sorry, you're at sine pi over 2, cosine pi over 2, which should bring you here. All right, so you could switch that and then do the shift, but then once you do the shift, you can simplify and it just becomes this again, I believe. Or maybe not. Well, anyways, there's multiple ways of doing it. You could shift it, and you could shift sine and cos and shift it by pi over 2, or you could do this. All right, there's, once again, many parameterizations for the same thing. But this is perhaps the easiest method of getting things to switch directions on a circle. Okay, so there was a question earlier. So there are 2 parameterizations for a circle. Not really, there are 2 orientations of the circle. You could go clockwise or counterclockwise, but remember, there are many more parameterizations, right? If you think of this, I could make t like t 300 times t, right? In which case, I have cosine 300t minus sine 300t. I'm still traversing clockwise, but eventually, intuitively, if I do 300t here, I'm actually traversing it a lot faster than I am if I don't add anything for the t. So there are really infinitely many parameterizations of the same path, even for the circle. It's just for clockwise and counterclockwise, you could kind of categorize them in similar ways. Right, so why is it minus infinity to infinity? That's convenient. Oh, well, it's because it's a typo. Thanks for chat. That's plus infinity. But what I'm doing here is really, I'm starting at t equals 0 here. I'm really spinning across this circle, either clockwise or counterclockwise, or both of these infinitely many times. So here's a question for chat. How should I alter this parameterization region t for me to traverse this circle once? So instead of minus infinity to plus infinity, which, if you trace it out, this is going to traverse the circle infinitely many times. If I just want to traverse the circle once, and I want to start at t equals 0 at this point, and I want to traverse it once, how should I alter the range of t? Right, so the range should be, I've got suggestions minus 2 pi to plus 2 pi, 0 to 2 pi, right? So it should be 0 to 2 pi, or minus pi to pi, right? I want a period of 1, right? So how do we traverse the circle in B just once? And the answer is to restrict to a period of 2 pi, right? So maybe let me specify first. And still with, let's say, sorry, my pen's not working. Right, so with the same starting point, or at 1, 0. So you could restrict to a period of 2 pi. So you could either do t is between 0 and pi, or you could also do t is between minus pi and pi. So if t is between 0 and 2 pi, well, then you start at 0 and then you go around, and then at 2 pi, you come back where you are. If you go from minus pi to pi, then in fact, you're starting at t equals minus pi is what your clock starts at. You still pass at t equals 0, you still pass through 1, 0, and then you go on until you end at pi again, which is back here. All right. Or you could also do various versions. You could do minus pi over 2 to, I guess, what was that? That's like 3 pi over 2, right? You could start here and go over here, start anywhere in the circle, but you could restrict to periods of 2 pi. So options. How do I now, okay, so part D of this, how do I just do a semicircle? Let's say I want to start here and I want to trace, let's say I'm in A again. I would just want this top semicircle here. How do I do that? Right, so I have a period of pi, so I could start at t is equal to 0, and then where do I end at? From 0 to pi, right? So t for A, restricting t from 0 to pi gives a semicircle. All right. Okay, so this gives an example of you have a parametrization given to you by a function of one variable into two variables, and then this single parameterization, this equation, when you think about it, depending on how you depending on what you restrict your one-dimensional domain, it traces out slightly different parts of your path. So you really get a lot of control, right? The algebraic equation for any one of A, B, C, and D is really just x squared plus y squared equals 1. But because you have a parameterization here, and also you could insert factors in front of t if you want. We didn't do this, but you could control how fast you're going around the circle by restricting the domain of t. You could control how many times or what portion of the circle that you're traversing. By subtly changing the parameterization, you could also reverse the direction you're going along a curve. All right, so parameterizations give you all these options of what a curve is, and they're really the right way of modeling how paths move through space. Let me conclude today with maybe another exercise. So let's say, so consider the following parameterizations. Let's say you have x and y are equal to t cubed, t squared. B, x and y are equal to t to the 6th, t to the 4th, and C, x and y are equal to e to the minus 3t, e to the minus 2t. So what are the algebraic descriptions of these curves? And I say t for all of these are going to be from minus infinity to infinity, plus infinity, sorry. And how do A, B, and C differ in the paths they trace out? All right, so let me give you a moment to ponder this. And I'll also answer Sean's question in chat. No, there's multiple ways to do the upper semicircle here, because you could traverse the semicircle as fast as you want. For example, I could do cosine of t. Let's say I could do cosine 2t sine 2t, right? For example, here I could do cosine 2t and cosine 2t sine 2t. I'm sort of going twice as fast, and in that case, I'll start at t equals 0, and instead of going all the way to t to pi, right? I only go to t to pi over 2, because at t equals pi over 2, if I have a factor of 2 here already, then at pi over 2 is pi over 2 times 2. So that's just pi, and I end up here, right? I got to, depending on how I parameterize this, I could parameterize the upper semicircle any way I want. In fact, I could put any function of t here and then do cosine of that function of t, sine of that other function of t. And that gives me a completely new parameterization of how I traverse the path on this circle. Right, okay, so we have some suggestions on this example. So the name of the game here is kind of to eliminate t, right? So maybe I'll just write this down. So to find the algebraic description, we need to eliminate t. So for A, we could try this, right? So if x and y, so if x is equal to t cubed, y is equal to t squared, what you could try is, well, so right, so x is equal to y to the 3/2 does work. Although when y is negative, then you got to take a square root, which isn't the best. But you could eliminate this issue by first squaring x squared. This gets you, if you square x, that gets you t to the cubed squared, which is t to the 6th. Y cubed gets you t to the squared cubed, which is 6. In which case, they're both equal to t to the 6th, and then you get a description x squared is equal to y cubed. All right, but this is also the same. It's also valid to write x is equal to y to the 3/2. But if you want to eliminate annoying things like half powers, then it's nice to have something purely algebraic like this. And what's b and c in this case? So for example, b, you could also do the same thing, right? Well, we could try something different. T6, y is equal to t to the 4th. And now, if you look at like a Muhammad's example in chat, then you could try the same trick, right? How is t to the 6th related to t to the 4th? Well, you also get the fact that you could do, let's say, well, let's find different ways of doing this. I don't want to repeat the point here. You need to generally be somewhat creative, right? X over y has a ratio of t squared, right? But what's t squared? Well, t squared is the square root of t to the 4th. So that's the square root of y. So that's y to the 1/2. So that gets you x over y is equal to 1/2. Is x over y is equal to y to the 1/2. Multiply both sides by y, and you get x is equal to y to the 3/2, right? Which, if you square both sides, they satisfy the same equation, right? And c, I'll leave you to check. They do the same thing. Any questions on the algebraic manipulation? I haven't addressed the second part of this, how they differ in the paths they trace out quite yet. Okay, so I mean, there are 5 minutes left. I think this is good enough. I think it's good enough for the first time. So can we just use the same reasoning for A for B? Yeah, you could use the same reasoning. There are many ways. So the moral of this is, if you're given parametrizations and you want to recover the algebraic description, which is kind of the more natural way we know how to imagine curves, right? X squared plus y squared equals 1 is easier to imagine than parametrizations, even though it gives less information. You really have to be creative in how you eliminate t. So you can eliminate t in however method you want to get this. All right, I was just showing a different way here. There's a subtle thing though, because you're given parametrizations here, they kind of give you different information, even though they have the same algebraic equation they satisfy. They trace out different portions of the curve, just like we had above, in terms of a full circle once, a full circle several times, a full circle clockwise versus counterclockwise, and portions of the full circle. So you got to be careful. So maybe next time, so tomorrow, let's start off class with figuring out how these paths differ in the paths they trace out. All right, so I'll leave you with this. I'll post these notes on Quarkus. Hopefully whoever recorded this to my cloud, I'll figure it out. I'll post it on Quarkus as well. And I'll see you tomorrow. Any questions? Could you get the original parameterization of the algebraic description? No, in general, right, there are many parameterizations for a given algebraic description. So if you're just given an algebraic description, there are many ways for you to parameterize something. It's very hard to get the original one. But from a given parameterization, you could always find an algebraic description given it's nice enough.